of this type. You would have terms of this type. Okay. Now you combine them. So you would have terms which are time boundary curve and space boundary terms. These terms would vanish on their own at the boundary because these guys vanish at the boundary. These guys would not vanish at the spatial boundaries. Okay. So our task is to make them vanish. So we have to choose the boundary conditions. You see, boundary terms and boundary conditions are related. Okay. Boundary conditions are dictated by the boundary terms. And we do not want to have any boundary terms in the variation of the action. Why? Because otherwise our action would not be Lorentz invariant. We would like to have Lorentz invariant action. Therefore, boundary terms which are going to spoil our Lorentz invariance, we make them 0 by hand, by choosing such boundary conditions which make them vanish. Okay, that gives rise to different kinds of string theories. Okay, that gives rise to different kinds of string theories because you choose different kinds of boundary conditions. Okay, so for open string you would consider different boundary conditions. For closed strings you would consider different boundary conditions. Okay, and they would so plus but time boundary conditions also let me remove from here. I can leave the space boundary terms. Okay, and plus you would have these terms and similarly some more terms which are of the type this was del tau of psi minus plus del sigma of psi minus into del psi minus. Okay, and here also into delta psi plus. This term could be combined, written into the light front coordinates as 2 del plus psi minus delta psi minus. Here it was delta psi plus. Okay, fine. Now we use our standard argument that these variations delta psi plus are arbitrary and non-zero. Okay. You see, in the variational principle, these guys vanish only at the extreme boundaries, not in between the variations. So if this guy is not 0, then this has to be 0. And that gives us one of the Dirac equations. Del minus psi plus equal to 0. Okay. If this is non-zero, then this has to be 0 and this is Dirac equation. Here, this guy is arbitrary and non-zero. And therefore, this has to be 0 and this gives rise to the Dirac equation. So we have two Dirac equations, del plus psi minus equal to 0, del minus psi plus equal to 0. We have been using them in the past because I had just mentioned that if at some point of time I would derive them. Okay, so now we have derived them and now we can, this part also we can forget. But now we come back to the last part, which is most important now, because we have these boundary terms, okay, and they have to vanish. So if you like, I can write them down on the top, because we would like to retain them for some time. These are the space boundary terms, okay, and the space boundary terms are space boundary terms, they are iota t by 2 d tau times, maybe you can take out the factor of 2 also. So psi plus delta psi plus minus psi minus delta psi minus, and this at sigma equal to pi, and this at sigma equals to 0. So if you like, I can leave it like that. If you like, I can write it twice. So this at sigma equal to pi minus this at sigma equal to 0. Okay. Now we have to go to different cases. How we make them vanish. Okay. And this would distinguish in the different kinds of string theories. So, for example, let us go to the open strings. Open strings. Now, here for open strings, for these things to vanish, okay, in open string case, these terms, they vanish individually. Okay, I mean 1 plus this minus this and this. Okay, so one choice is psi mu plus is plus minus psi mu minus. You see, in the open string we have two ends. One at sigma equal to 0, one at sigma equal to pi. Okay, and so we have to choose these boundary terms, boundary conditions at the two ends. Okay, because both ends are free, we have to choose these boundary conditions at both the ends. So in principle, I can take psi mu plus equal to plus minus psi mu minus, but and then at one end sigma equal to 0, and then I can choose at sigma equal to pi. But it is enough to consider just one. So let us fix this equal to this at sigma equal to 0. Let us fix this equal to this at sigma equals to 0. Okay. But then what happens at sigma equal to pi? So at sigma equal to pi, now I would have two possibilities. Okay. This is at sigma equal to 0. So this at sigma equal to 0 and this at sigma equal to 0. Okay. Now this gives me two possibilities. Then I choose plus at sigma equal to pi equal to plus minus of psi minus at sigma equal to pi. I first fix this sigma plus is plus of sigma minus. I am calling it sigma. I am sorry, I should call it psi. Psi of plus at sigma 0 is psi of minus at sigma equal to 0. Okay. This leaves me with two choices for the other end of the string at sigma equal to pi. In both cases, if I choose this equal to plus minus of this, if I choose this equal to plus, then also boundary terms would vanish. If I choose this equal to minus of psi minus, then also boundary terms would vanish. These two are called as, let me write small, and so when I choose the first choice, psi plus is plus of psi minus, these are called as Ramond boundary conditions. And when I take this equal to minus of this, they are called as Neveu-Schwarz boundary conditions. So the corresponding strings, because the mode expansions would be different in the two cases. In this case and this case, the mode expansions would have to be different. Our aim is to make these boundary terms vanish. Okay? We remember that our aim is that these boundary terms must vanish in all the cases, open string case, closed string case. In open string case, two different cases arise. At one end, I fix, for example, this equal to this. I could have also chosen this equal to minus of this equivalently, but then this might change. So if I change this, if I fix this equal to plus of this, in that case, I have to put this equal to plus minus of this. Plus choice is called as the Ramond sector and minus sign is called as the Neveu-Schwarz sector. Okay, so in these two cases, then we could write down the mode expansions for our psi. Okay, and so in the R sector, and it is called psi plus mu is defined by, these are normalization factors, and from the n is a real number, d mu n e to the power minus iota n into tau plus sigma n psi minus mu h